Now that we've discussed how to briefly assess relationships between variables just by looking at the data itself and by using a scatter plot, let's discuss how we can actually calculate a measure that focuses on examining just that. The correlation coefficient in statistics, symbolized as lowercase r, is a number between -1 and +1 that describes the relationship between a pair of observations across two variables. Keep in mind that the correlation coefficient only describes the linear relationship between pairs of variables for quantitative data. We will only be working with quantitative variables and only be assessing linear relationships. Other procedures can be used when working with other types of data or assessing different types of relationships. The correlation coefficient r can tell us both the direction and the strength of the relationship between variables. The sign of r, either positive or an implied positive sign, versus negative, indicates the direction of the relationship. The numerical values of r, not paying attention to sign, indicates the strength of the linear relationship between variables. The more closely a value of r approaches either -1 or +1, the stronger the relationship. The more closely a value of r approaches 0, the weaker the relationship. For example, in r of 0.95 indicates a very strong positive relationship or correlation, as this value is very close to 1. In r of 0.30 indicates a relatively weak positive relationship or correlation. In r of 0.01 indicates a very weak positive relationship, almost no relationship or correlation, as this value is very close to 0. In r of -0.24 indicates a relatively weak negative relationship or correlation, and in r of -0.80 indicates a relatively strong negative relationship or correlation, as this value is getting closer to -1. If we were to arrange these r's in terms of the strength of correlation from weakest to strongest, the weakest would be 0.01, followed by -0.24, followed by 0.30, followed by -0.80, followed by 0.95. When arranging, keep in mind that correlation coefficients may not be arranged in the same way as you would normally arrange positive and negative numbers, as the weakest correlation coefficients, or r's, are the numbers nearest to 0, either positive or negative, and the strongest correlation coefficients are the numbers closest to either 1 or -1. Let's talk about an example of a correlation coefficient using the previous example comparing miles from home to CSUN and midterm score in a group of 5 students. If we had used SPSS to calculate the correlation coefficient for this data, it would have given us an R value of 0.028. Since our correlation coefficient of 0.028 falls very close to 0, but on the positive side, we can say that the two variables we were looking at, miles from home to CSUN and midterm score, have a very weak relationship, and the direction of the very weak relationship is positive. Many would conclude from this very weak correlation coefficient that there is very little, if any, relationship between miles from home to CSUN and midterm score based on this data. Now that we've talked about the calculation of our correlation coefficient, let's jump back to a concept that we talked about very early on in the course, or outliers. Remember that outliers are defined as very extreme scores that require special attention because of their potential impact on a summary of data. Outliers can have a dramatic effect on the correlation coefficient, so a very important question is what can be done about outliers. If a mistake has been made that has caused the initial outlier, for example, an error in data entry that is later realized, that might be justification for discarding the outlier, particularly if you can go back and check to see if this value was in fact incorrect. For example, if you are looking at age at first pregnancy and you see one age recorded as 145, you can check the data for accuracy and discard this outlier as being misrecorded. If you cannot confirm that the outlier was misrecorded, however, and you are unsure if it is an actual value reported in your data, it is often recommended not to simply discard the value even though it might impact your study results. If this is the case, often the potential influential effect of any outliers is dealt with by reporting the value of R with and without the outliers included, and stating that you had an extreme observation in your data that affected results. So let's talk about the interpretation of R. If generalizations from sample data are to be made, R must be viewed in terms of both its value and the number of pairs of observations used in its calculation, so sample size should be taken into account. R should not be interpreted as a proportion or percentage of some perfect relationship. R is independent from the original units of measurement used in calculation, so will not have units such as pound, minutes, or inches, for example, attached to it. Therefore, a valid interpretation of an R equaling 0.65 between height and average daily calories consumed is people who are taller tend to have a higher daily level of calorie consumption, as our R indicates a moderate positive relationship exists between the two variables. You would not say 65% or 65 pounds. One very important thing to keep in mind is that a correlation coefficient of any value, even 1 or -1, never proves that an observed relationship between two variables reflects causality between the two variables. This concept is often summarized in the expression, correlation does not imply causation. Just because two variables appear to be strongly or perfectly associated or related based on your sample results, it does not mean that the change in one variable necessarily directly causes a change in the other variable. There could be bias present in your study, such as a confounding variable, that can distort results. While an R very near 1 or -1 implies a very strong correlation or association appears to exist between your variables under study and can be interpreted as such, it should not be interpreted as the change in one variable directly causes the change in the other variable.